The next topic is about p-values. All right. So we talked about p-value hypothesis testing last time, and I didn't really. So we already talked about p-values, but I'm going to have a special lecture just about p-values. Okay. And the reason why I want to have a special lecture just about p-values is because p-value. The fact that people do research and publish their finding whenever p-value is significant, okay, whenever p-value is below, let's say 5%, and they declare that significant and publish their finding, is very problematic. It's very problematic. There's a lot of problems of doing research, finding significant result, and publishing. There's a lot of problem with that practice. Okay, now and some problem is just unavoidable, but we try to. The purpose of this actually is to help you understand what are actually some of the drawbacks, what are some of the limitations of hypothesis testing and p-values? What are some of the limitations, and what are the common misunderstandings people have about it? Okay, so this is a very famous paper by Ioannidis. He published in the Medicine Journal, because this is a problem facing not only economics, but all scientific discipline that do research and finding significant results and publish. Okay, so that's a problem facing everybody. So that's what he said back in 2005, that there's an increasing concern that most published research findings are false. Okay? They're false not because they are incorrectly done, but because they publish based on p-value being significant, and in the end it doesn't really it's not really the case. Okay? So they make a type 1 error that they should not make. This is the article published by Andrew Xiamen, and Andrew Xiamen is a guy, he's a statistician at Columbia, who writes a very famous blog, okay, in which he talks about everything related to, he not only talks about statistics, but also economics, political science, right? He does a lot of social science thing, very interesting person. And he also loves to talk about psychology, not because he loves psychology, but he believes that modern psychological research is very bad, okay? So he likes to say that his favorite practice is to assign top journal articles in psychology to his first year stat students, and ask them to basically tell him how bad these articles are. Okay, and here is this is a published article. This is a published article. The first line, the abstract. This is the abstract. The first line is top journals in psychology routinely publish ridiculous, scientifically impossible claims, based just on p-value smaller than 0.05. Okay, so he's really out there and attacking psychology. Why? Why does he attack psychology? Because many articles in psychology does have problems, and here is a very famous example. Okay, here's a very famous example. This is an article published in 2011 by a psychologist at Cornell, right? Daryl Bem. And this article is published in the top journal, okay? The top journal of psychology, Journal of Psychology, American Journal of Psychology is like the AER in economics, right, for psychology. And his research shows that what? The article says his research shows that people can predict the future, okay? People can predict the future. That's called ESP. They have the ESP ability, which means people can sense the future when they're excited. And the way, obviously that's wrong. Okay? Obviously, this is a ridiculous paper, ridiculous claim. But this guy's published. And the reason why it's published is because, hey, it's statistically significant. Right? And how does he do it? Well, first of all, and this is a true story. That's the truth. He basically enrolled, many students, okay, from Cornell, undergrad students, and they put them in front of a computer. Everybody look on the computer. And so here's how the experiment goes. He tells the students, there are two windows, okay, in front of you. Of course, on a computer, digital, okay, digital. There are two windows in front of you. You are going to guess behind which window one of the windows there's a picture behind. The other window behind it there's empty, or it's completely empty. You are going to predict which window has a picture behind it. The two windows look completely the same. So that's it. The second thing is when the students make the guess, the picture has not been put into it yet. Okay, so it's after they make the guess, the computer is going to randomly generate a picture behind one of the windows. So essentially, he's telling students to predict the future, right? Predict which window the computer will put a picture behind. That's putting a picture, okay? And he finds that in one of his experiments, that 53% of students predict the true window, okay, the correct window, and 47% does not correct it, and that's significant. Okay, and there's even a funnier part. Okay, there's a funny part. He finds that if you put a picture that is pornographic, erotic, okay, like a nude woman or nude man, okay, just erotic picture behind the window, students are more, students have 53% students can predict that. Okay, students are easier to predict when a picture is erotic. If the picture is not erotic, then students 50%, it's 50%. So his interpretation is that when people get excited, okay, by the idea of seeing, nude people, they can predict the future. That's his claim. Okay, that's his claim. And obviously that's ridiculous, and that's completely untrue. There's no foundation for it, but it gets published because it's significant, right? So when this paper gets published, it gets a lot of press. Many media goes to the interview, not only him but also the journal editor, and say, why do you guys accept the article? Because it's so ridiculous. And the journal editor says, hey, it's significant. What can I do? It looks like it's a solid result. So what they are not understanding is that simply accepting a claim based on p-value smaller than 0.5 is a very bad idea. Okay, it's a very bad idea, and I'll explain why. But the first reason why, okay, the first very simple reason why. First of all, why could p-value be significant, right? Why could p-value be smaller than 0.5? Like why? Well, suppose your H0 is true, right? Okay, so suppose your H0 is absolutely true. It's equal to beta star equal to 0. There's no effects, okay? There's no H1 is false, beta 0 true. Suppose this is true. Okay? Which means what? Which means your t statistic comes from a normal 0-1 distribution, right? Okay. And then suppose you generate many data. Generate many data sets. And in each data set you are going to estimate your beta hat, okay? You are going to estimate your beta hat. And then you're going to determine whether beta hat is significant or not. How many times, how much percentage of times will you get significant result? Do you know? So I'm claiming that even if H0 is completely true, okay, beta star is equal to 0, you actually not often, but you can get significant results. How many percentage of time? Right? 5% of time. Why? Look, it's a normal 0-1 distribution. So if you try many times, you're going to have what? You're going to have values here, and you're going to have values here, right? Okay? And it's 5%, right? It's a 5%. So if you try many times just by chance, okay, just by chance, 5% of the time, you are going to get, even if this is true, so that the t-value is normal 0-1, even if this is true, 5% of the time, you're going to get extreme value t here, extreme value t here. So you're going to claim your result is significant, right? Okay? So just by chance. So just by chance, you can publish a finding like this, right? So, by the way, right, nobody has successfully replicated his experiment. Right? Not because we believe him, we trust him that he's not making up the data, right? Even if you believe him that he's not making up the data, he's completely honest. He does the experiment, he publishes finding. Even if you believe that, okay? Well, which you should, okay? He's there's no reason that he's a dishonest guy. Even if you believe that everything is honest, that just you could completely by chance that p-value is smaller than 0.5, right? Because it's very easy, completely by chance that 53% of time, 53% of population, the students choose the correct answer. It's just by chance, and then it will give you a significant result, and then you publish your paper and you get infamous. Okay, so this is the first reason why you should really be careful. But there's a deeper reason. There's a deeper reason why you should not trust fandom findings like this. Which is what? Which brings us to this topic. Remember last time I told you. We already have talked about it 2 times. Why do we have alpha, right? Why do we have alpha equal to 0.05 or 0.10 or something? The reason why we want to do this is based on decision theory, right? So I told you this too. So the idea is that suppose y, the true value y is +1, -1, and you want to make a prediction. Okay, your prediction is y hat, -1 +1, okay? -1 +1, right? So this is 0, this is your loss function, 0, 0 loss function. This is false, negative, this is false, positive, this is false, positive, right? This is false, positive. Okay. So we said we said that if you're concerned, if you treat false negative and false positive the same, if you think they're the same error, how do you predict y? Now suppose you know the distribution. You know the distribution y. You already know it. Do you predict y to be plus or to be minus? Okay. Now, py is between 0 and 1, right? This is py. Py is between 0 and 1. So if you treat the two errors equally, then what you should do is you should have 0.5, right? Above 0.5, you predict y to be plus 1. Below 0.5, you predict y to be minus 1, right? Okay? Very simple, right? So that's the best decision you can make. That's the Bayes classifier, right? That's the best decision you can make if you treat them seriously, equally. But if you suppose if you are really concerned about FP, false positive, you don't care about FN, right? False negative. What do? You should try very hard not to make a mistake. Meaning what? Meaning we should try very hard not to predict plus 1. You should only predict plus 1 when you are very, 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 very sure, right? Okay? So you should only predict plus 1. So what you should do? You should move your decision boundary, right? This is your decision boundary. So move your decision boundary to here, okay? To here. This should be a decision boundary. So everywhere here you should predict minus 1. And only what? Only here you predict plus 1. And here, what is this region? You can make it, for example, 5%, right? 5%. That's the alpha, right? That's the alpha, right? Our alpha come from. So you should only do this, right? You should only predict plus 1 5% of the time, not 50% of the time, because you are afraid of FP. Or, in terms of hypothesis testing, we call this type 1 error, right? If you only care about this, then you should only predict plus 1 5% of the time. In our setting, you should only accept H1 5% of the time. And then 95% of the time, you should keep your H0, right? You should keep your H0. But this is not what the p-value is doing. Okay? Why? Because when we make this decision, right? This comes from decision theory. When we make this decision, we're based our decision on what? On py, okay? On py. So if you know py, you make decision like this. Okay? You make decision like this. Now, when we come to hypothesis testing, what is our y? Y is what? Our py is what? Py is essentially the probability of H0 and H1, right? When y equal to plus 1, it's essentially H1. So beta star is not equal to 0. When y equal to negative 1, it's 0, which is beta star is equal to 0, right? Is equal to 0, right? In our hypothesis testing, this is our y. So the probability of y, essentially is the probability of H0, okay? Or the probability of H1, right? You know one, you know the other, okay? You know the other, right? So in other words, decision theory tells us, in order to make the best decision of whether you should accept H1 or accept H0, you should base your decision on what? On the underlying probability of H0 being true, H1 being true. Okay? So if the probability of H0 being true is as long as it is low, as long as the probability of H1 is smaller than 5%, okay? As long as it's smaller than 5%, you should accept H1. Otherwise, you accept H0, right? Okay? So you should base your decision on the underlying probability of H0 or H1. But is that p-value? No, that's not p-value. What is p-value? So I guess what I'm saying is, right now, what you're doing in statistics and econometrics is that you are basing your decision on p-value. And the p-value is not the probability of H0, right? What is p-value? P-value is the probability of your data, okay, your observed data, or t-statistic, right? T-statistic come from the data, right? So it's essentially the probability of observing your data conditional on H0 being true, okay? It's conditional. Suppose H0 is true. What is the chance of observing my data? Or what is the chance of observing my t-statistic being certified? That's what p-value is. But that's not something that you should base on your decision on. Your decision should be based on what? Should be based on the probability of once you see your data, what is the probability of H0 being true? Okay? That's what you should base on, right? Okay? Your decision should be based on the probability of H0 being true, conditional on the data, not the probability of data conditional on H0. Okay? Right? That's what decision theory tells. Okay? So this probability of H0 being true conditional data is like what? It's just like the Py we just described. Okay? And if you know this, then you can make decisions. Okay? Now, but what's the relation between them? What is the relation between p-value and this thing? Okay, and this thing. Well, right? We have the Bayes formula, right? So, given D, given my data, the probability of H0 is equal to what? Is equal to the joint distribution of D and H0 divided by PD, okay? Divided by PD, right? Divided by PD, which is equal to what? Which is equal to D conditional H0 P H0, okay? P H0, right? Do people know this? This is sort of the Bayes formula, right? It's Bayes rule, okay? Bayes rule. Now let me ask you, what is first of all, let me just describe it here, okay? Now, what is this? This is the probability of H0 being true. Once you have seen the data, okay? Once you have actually seen the data. Conditional on your data, what is your belief about H0? What is this? What is PH0? PH0 is before seeing the data, okay? Before you have seen the data, what is your belief about H0 being true? So, do you know what this is called in Bayesian terms? Have people studied any? Do people know any Bayes? No. Yes. So this is called the prior belief. Okay, prior belief, and this is called the posterior belief. Okay, posterior belief. And that's a Bayesian term. Okay, that's a Bayesian term. So the prior belief means you have not seen the data yet. Before you see the data, this is your belief. The posterior is after you see your data. After you see your data, you update your belief. Okay, your belief become new because you have seen new evidence, right? So give you an example. So this, this PH0, this prior belief may be, for example, suppose before you came to Xiamen University, you believe that there's no such thing as a black swan. Okay, suppose your belief is black swan doesn't exist. That's your prior belief. And you come to Xiamen University, you go to the Frozen Lake, you see there's a black swan, so you see the data, you update your belief, and then now you know, okay, black swan exists, right? So that's a prior and a posterior. That's called prior and posterior. All right? Okay. So we should what? We should make our decision. We should decide to accept H0 or accept H1 based on this one. Okay, based on our posterior belief about H0, not based on this p-value, because this is p-value, right? What is p-value? This is p-value, right? This is p-value. Okay? This is p-value. So we should base on this, not based on this. And by the way, I'm going to just delete PD here, okay? I'm just delete PD here, right? And I'm going to just write it as p-value, okay? I'm just going to write p-value, okay? P-value, right? P-value. So we should base our decision on this one, not on this one. Now, what's the difference, you ask? What's the difference between this one and this one? Right now, in what we're doing is that we're saying, okay, when p-value is small, I'm going to reject H0. I'm going to take H1. That's what we're saying. But when p-value is small, this probability of H0 may not be small, right? Okay. So in other words, p-value is not the probability of H0 being true. So when p-value is small, the probability of H0 being true can still be what? Can still be large. That's what this is saying. Okay? Even when p-value is small, the probability of H0 can still be large. So you should not reject it. Now, why would the probability of H0 be large when p-value is small? Because this pH0 may be what? May be large, right? So if this is small, this is large, we can still have a pretty large pH0, the probability of H0 being true, which means you should not reject it, okay? So that's the key message here. The key message here is p-value is not the probability of H0 being true. So when p-value is small, it doesn't mean the probability of H0 being true is small. The probability of H0 being true can still be pretty high. So you should not reject it. And what does it depend on? It depends on not the probability of H0 being true. Depends not only on p-value, but also on your prior belief about H0 being true. The prior belief means what you believed it to be the case before you see this data. Okay, before you see this data. So give you one example. Okay, give you one example how it works. Suppose my H0 is this. Suppose my H0 is people cannot predict future, okay? Suppose my H0 is people cannot predict future. What is your prior belief? What is your belief about this statement being true before you look at any data? 0.99999, right? Right? Correct? Nobody think it will be false, right? Of course, people cannot predict the future. By predict, I mean like sensing the future, right? Like sense how many, in which window, behind which window there's a photographic picture, right? That's what I mean by predict. So of course, this is you believe it's true, okay? So you believe it's true. So it's so prior belief of 0.009999. And then suppose you are Derek Bam, the psychologist. You go out and you do experiment, and your experiment you have some data. Okay, so once you have some data, the data tell you the p-value is smaller than 0.5. Okay, 0.5. The question is, do you accept or do you reject H0? Now the problem is this is close to 1. Okay, this is very close to 1. So this is very large. So even though this is small, this can still be large. By the way, there's a we divide by PD, okay? We divide by PD. So this is large, this is small. So this one, the probability of H0 conditional on seeing the data should still be very, very large, okay? Should still be very large. So meaning that H0 could still be very, very true. So you should now reject it. That's the fundamental problem of what Darrell Bam is doing, which is deciding whether you accept H1 or you accept H0 based on a single data set. When you should what? When you should consider all your prior information or what you believe before seeing the data. You cannot let a single data set determine what you believe about the world, right? Essentially, that's what it's saying. Essentially, that's what it's saying is your belief about the world should not be determined by a single data set. It should be determined by the data set and what you believe before. Because what you believe before is the history of thousands of years of human civilization and scientific discovery, right? So thousands of years of human civilization scientific discovery tell you that people cannot sense the future. Right? There's no such thing. Then you should, single data set with a small p, you should not suddenly overthrow that conclusion. Okay? All right? So that's essentially what this is saying, right? And this is essentially the Bayesian way of thinking. So this is not a frequentist way. Now, the reason why p-value is a problem, okay, deciding whether you accept H0 and accept H1 is a problem in our scientific community is because many people are doing the frequentist way, and the only frequentist way, okay, here's the difference between Bayesian and frequentist. Frequentist has to make a decision based on single data sets. So a single data set, you do analysis, you do hypothesis testing, and you have to accept H0 or H1. So frequentist way doesn't have the possibility to allow you to incorporate your prior belief and prior information into your analysis. That's what frequentist way is bad about. Okay? What Bayesian way is good about is allow you to incorporate your previous knowledge and allow you to update your knowledge after seeing your data. So the Bayesian way is this is what you believed before. So this is what you believed before. You see the new evidence and then you update your belief. So if you believe that's impossible for people to sense the future, and then you see some evidence, yes, maybe they can. Then you update your belief. Your belief will be what? Your belief will be very small update. So before it's 0.009, now you see some evidence, you say, okay, maybe it's 0.09. It's not 999 anymore, right? But you still believe it. It's just that it's weaker belief because you see some evidence. And then you do this again and again and again, right? Continually updating your belief. And that's essentially how human knowledge advances, right? So Bayesian is a more sort of like a scientific way of describing how we get to understand about this world and updating our knowledge. So why do we not just do Bayesian? The reason why we don't just do Bayesian is because Bayesian also has drawback. And the drawback is everybody has a different prior. Okay? Everybody has different belief. And there's no way to what? So you can do analysis saying, okay, my belief is this. And I reach a different posterior. Now your belief is this, you have a different conclusion. And the scientific community has no consensus, right? Because you can just say whatever about your prior belief, and then it's hard to get a conclusion about anything, okay, about anything. So that's the drawback of Bayesian. So nothing is perfect, okay? Frequentist is not perfect, Bayesian not perfect. You have a question?
Sorry,
yeah.
You have already answered my
Okay,
question.
great, all right. So, the next point I want to make is this. is this. So suppose we have to do frequentist, okay? Suppose we have to do hypothesis testing. What is a better way to do? Okay? Well, let me try some simulation. Okay, let me try some simulation. I'm going to simulate a problem in which my p-value, in which I know that my p-value ph0 is equal to 0.9. Okay, that's what I believe in. So I believe, so there's a h0 which I have a very strong previous belief in. Okay, prior belief in. So I believe in this h0. The probability h0 is 0.9. Now I'm going to try many different p-values. Okay, I'm going to try many different p-values. So p-value is from 0.0 to 0.1 all the way to some values. And based on my prior belief and based on p-value, I'm going to calculate the posterior probability. So I'm going to use this to calculate the posterior probability of h0 being true. Okay, h0 being true. All right. So I'm going to try this, and I get this curve. Okay, and I get this curve. Okay, I get this curve. So this is p-value, and this is the probability of h0 being true posterior after seeing the data. Right, and they have this they have this green curve, right, green curve relationship. All right. Now, right now, what we do in the scientific community is we determine whether to accept h0 or h1 based on p-value. But I just told you that's not the best way, right? Ideally, you should determine whether to accept h0 or h1 based on the probability of h0 being true, condition like posterior. Okay, you should do this. You should base your decision on this, not this one. Okay. So now the question is, suppose I have this. Okay, suppose I have this. Suppose I accept h0. Suppose I only accept h1 when the probability of h0 being true is less than 5%. Right? That's what we tried. That's what we should do. Okay? Accept h1 when this probability is smaller than 0.5. 0.05. Okay, 5%. Now the question is, if I do this, what is the corresponding p-value? Well, look. So I go here. Okay, I go here. 0.5%. Go here. I take it down. The corresponding p-value is here. And this value is what? This value is, the corresponding value is 0.004, okay? 0.004. It's not 5%, it's what? It's 0.4%. Okay? Meaning that if this is what we should do, then if we're trying to do it on p-value, we should only accept h1 when p-value is smaller than 0.4% and not 5%. So we should have a much smaller p-value in order to accept my h1. Okay, so that's what it's saying. Why? Why do we have a much smaller p-value than 5%? Because I actually really believe in my h0. Okay, so I have a very strong belief in h0 being true, my prior information. So that's why I should accept h1 with a much smaller p-value. That's what we do. Okay, so in other words, so let's come back to Darren Bam's research about people can sense the future, right? If you very strongly believe that people should not be able to do that, so you believe that h0 has a very high probability, then you should only declare your finding to be significant when your p-value is smaller than 0.001% or something, right? So you should so in other words, if you have a strong prior belief in your h0, then your alpha value, right? Your alpha should be much smaller than the traditional 1%, 2%, 5%. In other words, you should only accept h1 when the evidence is really strong. Okay? That's what essentially what I'm saying. Right? Okay? Right? Yeah.
As you mentioned that if we increase our probability under h0 prior probability, so let's say this is my belief,
Yeah.
0.9999.
Yeah.
So it means that then there is no such reason to make any type of research
Why?
for testing my hypothesis, because I already know that the probability of h0 is 0.99.
Sure. Essentially, that's why, very good, right? That's why in Bayesian, if you do Bayesian approach, if you use Bayesian statistics, then you don't do hypothesis testing. Okay? Bayesians don't do hypothesis testing. Only frequentists do hypothesis testing. Because why? Because frequentists try to make conclusion about a statement, like a hypothesis, based on a single data set. Right? And then they try to guess what's going on in the underlying population. Bayesian is just continually updating your probability. Okay, just continue updating your posterior. There's no reason to do any hypothesis testing. Okay, so I hope does that answer your question? Yeah. Okay, so right. So like I said, Bayesian don't do this. Bayesian don't do this. It's the frequentist way of doing this, and the frequentist way of doing this has problems. And the problem is p-value, again, is not the posterior probability of H0. So you have so you basically you end up with very easily accepting a lot of things when you should not. So the key message here is ideally your alpha, if you have to do hypothesis testing, then ideally your alpha should be what? Should be not just be a constant. Okay, your alpha is what, like a threshold. Okay, so ideally we should just say, okay, below 5% significant, above 5% not significant. Ideally we should not do that. Ideally we should change our threshold based on the problem. If a problem is we strongly believe H0 to be true, then we should change alpha to be a much smaller threshold. If we believe H0 to be very much unlikely to be true, then we can increase our alpha value, right? So our alpha ideally should be based on a problem, not just a fixed value of 5%. But in reality, it's hard to do, okay? It's hard to do because, again, if you want to change your alpha value constantly based on a problem, then you are, again, asking people to what? You're asking the scientific community to, again, enforce some kind of prior belief, right? Because this alpha value comes from your prior belief of a problem, but everybody has different prior. Everybody can claim to have different prior. So it's very hard to actually, so it's impossible to do this in reality. So in reality, we still use p-value. And just unfortunate, okay? There's nothing around it. But the hope is you recognize its limitations. And the hope is you're able to read existing research, okay? You're able to understand and read existing research with the understanding that there is such a limitation there, okay? So the next time you see, a very impossible claim, like something that people can sense the future, or the dead man can walk. Anytime you sense this incredibly impossible research with a p-value being significant, you should know, right? You should know this. Okay, you should know this. You should basically understand that this claim should still not be believed. Okay, so that's one of hopeful lesson of this. Okay, all right. What time? Now, another limitation of p-value, like I said already last time, right? So when we talk about linear regression, I said the hypothesis testing nowadays is based on asymptotic theory, right? So we use CLT, central limit theorem, to derive the large sample property of p-value of t statistic, which is a normal 0,1. But this normal 0,1 is only correct in large samples. In small samples, it's not correct. Meaning what? Meaning the p-value you calculate, okay? The p-value you calculate is only good for large sample, not for small sample, right? But then here's the irony, right? Here's the irony. The irony is when n is small, okay, when your sample is small, your p-value is probably not very good, so it's not to be trusted. What about your sample size large? Well, if your sample size is very large, then your beta hat basically converges to the true beta, right? With very small variability. Okay, so what do you get in terms of beta hat is already very, very close to beta star. So there's no need to do hypothesis anymore, right? Remember, the whole purpose of hypothesis testing is what? Is you observe a beta hat and you want to learn something about the beta star. You want to make a statement about it, beta star. Why you want to make a statement about beta star? Because beta star and beta hat could be different, right? Could be different because beta hat come from a limited finite sample. But if your n is really large, then beta hat should be very close to beta star. So there's no need for p-value, right? So here's the irony. When n is small, p-value is not good. It's not to be trusted. When n is very large, p-value is useless. You don't need p-value. Okay? So what is p-value good for? It's really only good for the median, right? It's really good for the median. It cannot be small, but it's useless when you have too big, okay? Or too big problem, right? It also says what? It also says that for a long time, okay, for a long time, statisticians, okay, people in statistics, really concerned about hypothesis tests. Okay? Really concerned about hypothesis tests. They spend a huge amount of time trying to decide how to do what, how to do this inference, how to infer about the underlying beta star from beta hat. That's the inference problem. The inference problem has been occupying statisticians for as long as statistics is out there. But people in machine learning, for example, don't really care that much about inference. Okay? They don't care. They just want to predict and they're done with it. Okay? They get some estimate. They don't really care about the inference problem. And one of the reasons for that difference in philosophy is because machine learning is born out of modern computer science and the modern data science where we have a huge amount of data. So one of the insights is what? One of the insights is if you only have limited data, then hypothesis testing becomes important because whatever beta hat you get could be very different from beta star. So you want to do a hypothesis test, you want to make a statement about beta star, right? So you really want to do it right. So there's all this research, all this theory about how to do hypothesis test. But all this problem will be gone, okay? Once you have many more data, because if your n is very large, there's no need to do any hypothesis because what your beta hat is very close to beta star. Okay, is very close to beta star. So there are two ways to solve this problem of beta hat being different from beta, right? So if your concern is my beta hat is different from the beta star, okay? So if this is your concern, there are two ways to solve the problem. The first way is to try to improve your methodology, to improve hypothesis test, so that once you see the beta star, you can try to guess what beta hat you can try to guess what beta star is. This is one way of solving the problem. The second way, you don't care about methodology, you just go and get more data. Okay, just go and more data. Just get more and more data. So if you have more data, then of course, then naturally beta hat converge to beta star. So you no longer have any need to do any theory or any statistic, theory about inference anymore, right? So that's essentially the key sort of philosophical difference between the two disciplines nowadays. Because one discipline says we just get more data, okay, and we don't care about inference. The other discipline traditionally has been very focused on inference because they have traditionally been working with very limited data. Okay, all right. Now, and here's this is a slide taken from Andrew Xiamen. So, like you said, Xiamen doesn't like psychology very much. So this is taken from his slides. So in his slides, he takes this issue of psychological science, again, the top journal in psychology, and there are a bunch of articles published, right? There's a bunch of articles published. So, for example, this article says what? This article says visualize heartbeats, alter bodily self-consciousness. So if you let somebody see his heartbeat, right? Visualize it, okay? Just visualize his heartbeat. That will change his behavior. Okay, that's what this research is about. The second research is saying, I age in 5 years in 5 minutes. The effect of taking a memory test on adults' subjective age. Meaning what? Meaning you give somebody a memory test, and suddenly they think they're much older. Okay, that's the second research, right? So that's what the psychological research is about. Guess they're all statistically significant, published at a p-value below 5%. But look at their sample size. The first sample size n equals 17. So this guy literally published an article in the top journal in psychology by doing experiment on 17 people. And I find the p-value below 5% and published this article. Right? Can anybody trust this? Of course not. Okay?
It means that in psychological journals, there is no statistician for reading the paper.
Well, they are. I mean, they're catching up. Okay? They're catching up. They're because people like Andrew Xiamen has been attacking psychology. Psychology has been trying to improve themselves, right? So they're facing a lot of attack from other people. So this n is 17. This n is 57. Not good at all. Okay, even 57 is too small. So you have all these papers being published in top psychology with like 17 data points. It's crazy, right? Even for economics. Okay, economics doesn't have large data, but even we think it is crazy. So that's why it gets published, it gets attacked a lot. Now in economics, the problem comes now from microeconomics, right? So this is supposed to, in economics, the problem mainly from macroeconomics. Where in macroeconomics, if you want to do things like monetary policy, you want to say, okay, how when the Fed gets a certain, let's say, suppose I do quantitative easing, and what's the effect on the monetary policy on GDP growth, on employment, then your data is also very limited, right? Okay, because it's basically every year you get like a quarterly GDP data and a quarterly employment data, and the 4 data points for a year, and for a single country, that's very limited data. So that also makes it very hard for you to get any true knowledge because the data is limited. Okay, but anyway, so we'll stop here today and continue next week. Two more things I want to say is that's actually for next homework, not for this one. But so I have updated my homework guideline. So if you have not updated your homework guideline, you should go and update it. But the update is mainly about how you do your homework in the future, not for this one, because our first homework we should do this weekend is only theoretical, right? But if you want to do empirical, so starting next, because next homework is going to be empirical. Okay, not going to, but you can write empirical things. Okay, all right. So if you want to write empirical things, so if you do theoretical, you should write in LaTeX. But if you want to do empirical, you can write in R Markdown or you can write in Jupyter. So in Jupyter Notebook, you can use Jupyter Notebook to either write R or write Python, right? So you can do anything. I will give you extra 0.5 points if you do any one of them. Okay, if you're writing LaTeX, if you're writing R Markdown or Jupyter Notebook, you can basically get 0.5 extra points. Now, but they are not, you cannot add them. Okay, you cannot write one line in R Markdown and one line in Python, right? Like this guy has suggested, I think, right? You cannot do that. That's not stackable. But what is stackable is if you also publish. If you publish on if you have a GitHub page and you publish it, you also get 0.5. Okay, 0.5. Last time I said 1 point, but I changed it to 0.5 because once you have set this up, you can do it forever, right? So I don't want to give you 1 point forever. And finally, if you analyze real data, because the things you can do is you can do a theoretical report like the first time. You can demonstrate a method. Okay, by demonstrate method I mean take whatever we do in class and method we introduce in class. Simulate, okay, just simulate data and do it yourself. Or you can take my example, okay, whatever I have to write my example, you can translate it, right? So that's what I said. So that's called method demonstration. Or you can go and get some real data and apply whatever we talk in class, the method, to the real data. So if you do real data, you get 5 point more, okay? You get 5 point more. And then it's also stackable, meaning if you do real data and you're writing, like a LaTeX, then you get double, like you get 1 point, okay? You get 1 point. So that's what I'm going to say. And if you go to my lectures, right? If you go to my lectures, the thing here is you can click on any of this. So for example, we just finished regression today. So we have some R codes, we have some Stata codes, we have some Python codes. I haven't really written much about Stata, okay? So Stata is a very simple thing, just showing you, if you want to calculate robust Stata errors, it's very simple in Stata. But anyway. Because I haven't really written much in Stata, you can basically, you can do the translation work, you can write Stata and you give you points, okay, give you points. The data here, however, so the codes here contain only codes, there's no data. For the data I'm using these codes, you have to go to Moodle. So I keep the data in a different place, okay? So you go to Moodle, there's a data folder, you can download the data to be used for these codes if you want to see how these codes work. Final announcements. Tomorrow there's going to be another review session this week. Shitie will basically present a review session, and so he will walk you over some codes and he will talk to you and he will introduce things like Jupyter Notebook and stuff like that. Okay, so that's for tomorrow, and he will make a separate announcement in WeChat. All right, that's